Hello everyone, welcome to my class. In today's class, I'm going to cover exponential functions. So let me start the class right away. First, definition of exponential functions. An exponential function has of the form f of x equals to b raised to the power x. So here, x is an independent variable and b is a constant. X is real number and b is strictly greater than 0 and b not equals to 1 is called the base. Quick note, so the reasoning why we need b is strictly greater than 0 and not equals to 1. Let's suppose b is negative. Here I assume b equals to negative 2 and let's say x is 0.5, that means 1/2. Then negative 2 raised to the power 0.5, that means negative 2 raised to the power 1/2, that means under the radical of negative 2, which gives us a complex number, that means this is not a real number. And also, if b is 1, then our exponential function is reduced to identically 1. This is a horizontal line, and by the way, this is not 1-to-1, and we're not interested in such functions. Quick example of exponential functions: 2 raised to the power x, 2 raised to the power negative x, 5 raised to the power x, e raised to the power x, and so on. Alert, the exponential functions 2 raised to the power negative x is not the inverse of 2 raised to the power x. Great. So let's do example 1. Example 1, graph fx equals to 2 to the power x and fx equals to 2 to the power negative x. So let's use a tabular method. Make a table. First column x values, second column the 2 to the power x column, third column 2 to the power negative x column. So x is an independent variable, so we can pick x values. So let's pick some negative numbers as well as some positive numbers. If you pick x equals to bigger number, then your computations to compute the y values will be messier. So let's pick a smaller number for x. So here I picked x equals to -2, -1, 0, 1, 2, 3. So let's find the corresponding y values. So here, when x is negative 2, then 2 to the power x becomes 2 to the power negative 2, which is same as 1 over 2 to the power plus 2. That means 1 over 2 square. That means 1/4. That means 0.25. Similarly, when x is negative 2, then let's evaluate 2 to the power negative x. So then this becomes 2 to the power positive 2. This x minus and this minus gives us plus here. So 2 square is 4. Awesome. Now similarly, let's compute when x is negative 1, then 2 to the x turns out to be 0.5 and 2 to the power negative x turns out to be 2. When x is 0, then 2 to the power 0 turns out to be 1 and 2 to the power 0 turns out to be 1. Awesome. So now similarly, let's say when x is 3, 2 to the power 3 is 8 and 2 to the power negative 3 is 1 over 8. That means approximately 0.13. Great. So now let's plot those points on the graph. So in the first graph, we are plotting the point for y equals to 2 to the x. So the point is -2, 0.25. So here's -2, 0.25 here. Next, -1, 0.5. Here is a -1 and 0.5 right there. Similarly, 0, 1. So 0, that's the origin, and 1 you need along the y-axis. and so on, and join those points. Then this gives us a graph of exponential functions 2 raised to the power x. I hope this makes sense to you all. Now similarly, let's graph 2 to the power negative x. Now let's plot those points here from this third column. That means the first point is negative 2, 4. So let's go to the second diagram here. Here is the origin, here is the negative 1, here is the negative 2 here, and go 4 unit up. 1, 2, 3, 4. That's the point. Then negative 1, 2. Let's go again in the second diagram here. Negative 1 and 2. Similarly 0, 1. So 0 means at origin, and 1 just go along the y-axis upward. And let me graph the last point here. 3, 0.13. So here, from here, 1, 2, 3, and 0.13, somewhere tiny, little bit up there, and join those points, and this gives us the graph of 2 raised to the power negative x. So by looking at this 2 graph, the graph of 2 to the power negative x is just a reflection of 2 to the power x across the y-axis. Awesome. So I hope this graph makes sense to you all, and this idea of graphing exponential function makes sense to you all. Now let's move on. Now quick summary here, and as well as the side notes. First, summary. For the exponential functions, our domain is all real numbers. This is defined on all real numbers, and the range is 0 to infinity. That means x-axis is a horizontal asymptote for exponential functions. So the range is 0 to infinite. Function is increasing. So function is 1 to 1 because it passes the horizontal line test. So every horizontal line crosses this graph at only one point. Awesome. And its y-intercept is 0, 1. So it crosses the y-axis at 1. HA is x-axis. That means y equals to 0, and the function is continuous. Side note, fx equals to bx is a parent functions. We use it in transformations to graph various exponential functions. Point 0, 1 is the reference point on the graph, and fx equals to, if I take a e base for exponential function, that is e raised to the power x, this is called the natural exponential functions, where the number is 2.7182 ... Great. Next, let's talk about properties of exponential functions. So if we multiply the two exponential functions with the same base, then we copy one base and we add the exponent. If we divide an exponential function by another exponential functions, then this fraction equals to one common base and raise to the power x minus the exponent of the denominator's exponential functions. That means b to the power x minus y. If we raise the power of exponential functions, then we simply multiply the powers and we distribute here the exponent, and here's b to the power minus x is same as 1 over b to the power x, and similarly the last property. Awesome. Now let's move on. Next, the uniqueness property of exponential equation. If you have a two exponential function with the same base, then the exponent are equal. Awesome. Now let's use these properties and solve some example. Let's do example 2. Solve the exponential equations. Part A, 32 raised to the power x equals to 16 raised to the power x plus 1. And in part B, This is the natural exponential functions equations. So let's begin the solutions. So part A, we need the same base on both sides of this exponential function. So on the left side, let's rewrite 32 equals to 2 raised to the power 5, and then the exponent x as it is, equals to, rewrite 16 equals to 2 raised to the power 4, and x plus 1 exponent as it is. Then here we can multiply this exponent. So 2 raised to the power 5x equals to 2 raised to the power 4 times x plus 1. I hope this makes sense to you all. I use this property here. And then next, now by this uniqueness property, if you have the two exponential functions equal with equal base, then we can equate the exponent. So by the uniqueness property, simply the exponent 5x equals to the exponent 4 times x plus 1. Awesome. Now this looks like algebraic equations. Let's solve for x. So first FOIL 4x plus 4, then subtract 4x from both sides, then 5x minus 4x gives you x equals to 4. So we found the answer, x equals to 4. Great. Now let's move on. Now part B. So what's our question? Our question is here. So the first step, multiply this 3 to this exponent, and then bring this e to the power 2 to the numerator by switching the sign plus 2 minus 2. Then here, I think this is better. So then e to the power 3 times 2 x 6x minus 3 times 4 is 12 equals to e to the power x plus 5 as it is. Then bring e square to the numerator by making exponent negative 2, and then add to the exponent. That means here's minus 2. I hope this makes sense to you all. Then again, using uniqueness property, our exponent are equal. So that means 6x minus 12 equals to x plus 3. So then let's add the like terms. So I can subtract the x from both sides. I can add the 12 both sides. Then 6x minus x gives you 5x on your left hand side, and on your right hand side 12 plus 3, 15. Then to find the value of x, divide both sides by 5. This gives us x equals to 3. I hope this makes sense to you all. Now let's move on. Next, graphing exponential functions using transformations. That means without plotting the points, and the transformations means we are shifting either right or left, or reflecting across any lines, or stretching or shrinking. We're also shifting up and down. So let's use those transformations to graph the various exponential functions. First, some ideas. First, plot the reference point 0, 1. That's the point on the y-axis, and the HA means horizontal asymptote of exponential function is simply the x-axis, means y equals to 0. On the graph of the parent functions, that's exponential functions, show the transformations of them with respect to each transformations applied. That means when you shift, or when you reflect, or when you stretch, or when you shrink the parent functions graph, then what's the effect of those transformations for these two, the reference point and the HA, and then graph them, and after your final transformations, that will be the graph of these shifted exponential functions. Awesome. So now let's do example 3. Graph the exponential functions. Here our exponential function is given as 2 raised to the power x plus 1 and minus 3. So the idea, so let's begin the solution. So here 2 raised to the x is our parent exponential functions. Then we add 1 on the x coordinate. That means we shifting 1 unit to the left. And then we are subtracting 3 from the y value. That means we are shifting the graph of this 2 to the power x plus 1 3 units down. So that's the idea. So let me break down those transformations here. Start with the 2 to the power x, then add 1 on x coordinate. That means shift to the left 1 unit, and then subtract 3 from this y values. That means shift the graph 3 unit down. Then what's the effect of those transformations on our reference point? So here 0, 1 point lies on the graph of 2 to the power x. So in this transformations, in the first transformation here, so we add 1 on the x coordinate. So that means we are shifting the graph to the left. That means I am subtracting 1 from 0. That means I am going to the left. So here is a -1. I don't do anything on this y coordinate. I hope this makes sense to you all here. Similarly, in our final transformations, we are shifting the graph 3 units down. That means we are subtracting 3 from the y coordinate. So we're not doing anything for the x coordinate. So the x coordinate as it is. So for the 1 minus 3 gives you -2. So this is our new reference point for these exponential functions. Great. Similarly, for our horizontal asymptote, let's start with the HA y equals to 0. Then in our first transformations, we shift the graph 1 unit left. So we're not touching our horizontal asymptote. And in our final transformations, we shift the graph 3 units down. That means we are shifting our HA also 3 units down. That means y equals to -3. I hope this makes sense to you all. Now let's use these two informations to sketch the graph of this given exponential functions. So here, so -1, -2. Here is a -1, -1, -2. This is the point -1, -2. And y equals to -3 is this horizontal asymptote. So our then exponential functions graph looks like this. I hope this makes sense to you all. So now here the domain doesn't change, still the whole real lines, but the range is from -3 to positive infinity. 3 to positive infinity. Great. I hope this makes sense to you all. Now let's move on. Let's do example 4. Graph the exponential functions. Here the exponential function is 4 times e to the power -x minus 1 minus 5. Let's begin the solutions. Now start with the parent functions here, which is e to the x. Then multiply by minus to the x coordinate. That means we are reflecting about the y-axis. Then subtract 1. That means we are shifting the graph 1 unit to the right. And then multiply by 4 to the y value. That means we are stretching along the y-axis. And then next we are subtracting 5 from the y value. That means we are shifting the graph 5 units down. Now let's see the point. Here's our reference point 0, 1 on the graph of e to the power x. So in the first transformations, we multiply by minus to the x coordinate. So then 0 multiply minus is again -0, which is 0. So here's the point as it is. And in the next transformations, we are shifting the graph 1 unit to the right. So the x coordinate changes 0 to 1, the y coordinate as it is. And in the next transformations, we multiply by 4 to the y value. That means we are multiplying the y coordinate by 4, keeping x coordinate as it is. I hope this makes sense to you all. And in our final transformations, we are shifting the graph 5 units down. That means I'm subtracting 5 from the y coordinate, keeping x coordinate as it is. So here's 1 as it is. 4 minus 5 gives you -1. Great. Similarly, let's see the horizontal asymptote. Here's y equals to 0. Then here we are reflecting about the y-axis in our first transformation, so HA remains itself, and in the next transformations we are multiplying by 4 to the y value, so again HA remains itself, and then the final transformations we are shifting the graph 5 units down. That means our horizontal asymptote also shifted 5 units down. Great. So now let's use these two informations to sketch the graph of this given exponential functions. So here, that's better. So the point 1 minus 1 is here, and y equals to minus 5 is here. Then this is our exponential functions graph. Great. Again here domain doesn't change, so the range is -5 to positive infinity. I hope this makes sense to you all. So now let's move on. Remark: one very practical application of the natural exponential function involves the Newton's law of cooling. So the formula for Newton's law of cooling is T equals to TA plus T0 minus TA times e to the power negative kx, where k is positive. So here T0 is the initial temperature, and TA is the temperature of the surrounding, and Tx is the temperature x minute later. Great. So let's do example 5. A pie is taken from the oven when it is at 250 degree and is placed on the counter to cool down, where the air temperature is 40 degree and the cooling rate for the pie is 0.45. So the question is, what is the temperature of the pie after 2 minutes? Great. So now let's apply this formula and answer this question. So here the formula is, which is here, and now here after 2 minutes, that means x equals to 2, and here's our TA. The temperature of the surrounding is 40 degree, initial temperature is 250, k is 0.45. Then let's multiply here. So multiply this exponent, subtract these two values and simplify, and this turns out to be, after 2 minutes, the pie temperature is 125 degree. Great. So I hope this makes sense to you all. So now let's move on. So here is our final remark. Don't get confused with exponential functions with the polynomial or algebraic functions here. For example, y equals to 2 raised to the power x. X is an independent variable, is at exponent, and here x is the independent variable, which is the base, and 2 is the exponent here. So let's compare the graph. Great. Now let's graph those functions. So here in the first diagram, I graph y equals to 2x. I think this we already graphed before. And in our second diagram, I graph y equals to x square. So it's easy to graph using those tabular values here. And then here is y equals to x square. It's a parabola opening upwards, passes through the origin. So now let's compare these two and our final observations. The exponential function grow faster than the polynomial functions. So here in the same grid plane is the exponential functions graph. So if we increase the base on the exponential functions, the graph increases faster to infinity. This is our parabola, y equals to x square. Both are increasing, but exponential function grow faster than the polynomial functions. And also, by the way, if I raise the power here, x to the power 4 or x to the power 6 on our polynomial function, it goes upward, but with a flatly up. So it's a more goes this way and that way. So that's the idea. So I hope this makes sense to you all. We finish these sections. So thank you.